So we were talking about the fact. So by the way, what was the alpha? Right. Okay. So alpha is ARB. So now is alpha, which is ARB, is it entailed according to this whole thing we did? Is it entailed or not? It is, right? I mean, that's the whole reason to do this. So it is entailed. Okay, here's my question. Suppose you only knew about your world A or C and B or not C. A friend came and said, hey, I checked around the worlds that you possibly are in. I just found out A or C is also true about your world. Did you understand what I just said? Is your friend giving you any information? Is your friend giving you any information? The way you would be giving, they would be giving information is if you now know more about your worlds. That means the number of worlds you can be possibly in has reduced. That's how you become, you learn. Learning knowledge is identifying the world you are in closer and closer. If your friend came and said when you thought A or C or B or not C, okay, just a second, that I'm pretty sure that in the world you are in, A is true. Suddenly they gave you more information. But if they told you A or C is also true in your world, they didn't give you any more information. So not every sentence that I add is knowledge. The extra sentence that I added here, A or C, is not knowledge to me because it is in, another fancy term, deductive closure of what you already know. ARC is in the deductive closure of what you already know. But just because it's in the deductive closure, did you actually know it? I'm now talking nonsense, right? Know it means you might know the answer to a question, but you don't know that you know the answer to your question. Right? For example, if I were to ask you, would you know the answer to 957 times 845? You know that you would know the answer, but you may not know right away what the answer is. Because it's in the deductive closure of your math, assuming that you know numbers and you know multiplication, it's in the deductive closure of your knowledge. So on one hand, you would say that you got more knowledge if it is a sentence that wasn't actually something that I could have derived before. If I could have derived it myself, then it's in the deductive closure. But on the other hand, oftentimes deriving something is actually quite hard. Given the rules of chess, whether or not you're going to lose a game is in the deductive closure. But do you know? You have to compute. Basically, you have to do theorem proving. So it's worthwhile understanding that whatever is the theorem, so in fact ARB is true, this is a mini theorem that you prove to yourself. And so you get to add it to what you know. Given what you know, ARB also holds. And so you might as well just throw it in. Okay? It's worthwhile understanding that point, that anything that you prove to be entailed is now part of your knowledge base. Without even opening your eyes and looking at the world anymore. Just knowing what you know, this additional thing just follows by the rules of logic. And if it follows from the rules of logic, that means you haven't reduced any number of words. It's exactly the same number of words that we're holding with the knowledge base. But you may still want to memorize this. You want to write it down so that you don't have to rederive it very quickly, very slowly later on. So that's a very useful thing to understand, that sometimes knowledge is in your deductive closure. Sometimes it's additional knowledge, that means it's telling you more about the world you are in by cutting down some of the world that you can't be in. So it's a strange thing I'm telling you, that knowledge tells you if I give you non-deductive closure knowledge, it should have reduced some word that you thought was still possible. Do you understand what I'm saying? Yes, there was a question. Good. Okay. So it was in the deductive closure. Okay, the answer. Anyway, so that's what I just remembered. So now I'm just going to do the inference rules, which is like easy stuff for us mostly. So the inference rules, you know A or B, I'm sorry, A implies B, and if A is true, then you can just write B is true. You know this. That's an inference rule. Now my first question is it sound? Is it sound? That means what you are doing, would you have been able to do it if you tried to do it from first principles? To prove that an inference rule is sound, you need to draw the truth table again. So A, B, okay? So A is true, B is true, A is true, B is false, A is false, B is true, A is false, B is false. And those are your words. Okay? In each of these words, I happen to have, the knowledge base I happen to have is A, and A implies B. Those are the knowledge base sentences. I'm doing it slowly just to prove it once. Then you can start using modus ponens every time. Okay? So A is true, of course, in these words, and false in these words. Right? Now what about A implies B? You need to write this one. What is A implies B? It's useful to remember that A implies B is nothing but not A or B. That is what A implies B is. Okay? So, if not A or B, in this, is it true or false?
True.
True. How about here?
False.
False. How about here?
True.
How about here?
True.
Okay? So, true, false, he said, right? True, true. So then I make one more state thing for KB. KB is nothing but this and this, those two. Right? So it's true here, false here, false here, false here. Agreed? Okay? Now, I'm not done yet. Now I one more column for B. Because that's the theorem that you want to prove. Okay? And B happens, that's the column for B. And B is true here, because B is true here. B is false here. B is true here. B is false here. Okay? So now, all I need to do is check the rows where knowledge base is true and make sure that in each of the rows where knowledge base is true, B is true. Is that true? This is how you prove to yourself that an inference rule is sound. You do it once in your life and after that you just keep using it. Because instead of saying A implies B and A, B is true, if I now tell you P implies Q and P, you can still write Q. Because the name of the proposition doesn't matter. So you just prove to yourself that using this like first principles way, once you prove to yourself that the inference rule is actually sound, that means whenever it says the theorem holds, it is also holding because of the entailment, from the entailment side. Did you guys get that? Okay? Now of course, if you are into it, you can also write one more column which says KB and not B. And that will be all false all the time. That's a different way of proving the same thing. Okay? So that is modus ponens. There is another thing called modus tollens, which basically says A implies B and not B, then you can write not A. Okay? And in essence, actually, so that's, you can kind of see why, right? Because it's A implies B is nothing but not A is true or B is true. Okay? And if you are saying not B is already true, that means B can't be true. That means not A must be true. That's what modus tollens is saying. Okay, all these great names come from Latin because they were like existing for a long time. Nobody talks in Latin anymore, right? Then there is abduction, which says A implies B and not A means not B. Actually, in fact, a better version of, in fact, another version is A implies B, B is true, so A must be true. That's actually abduction. I don't know why I wrote this. It's kind of wrong. Okay? A implies B, and B is true, so A must be true. Okay? Basically, if I am, if I have flu, I'll get runny nose. I have runny nose, so I must have flu. Right? Now the question is it a sound inference? No. And you should be actually able to prove that it's not a sound inference. You should be able to prove that it's not a sound inference in this way. You will find that there is a row where A implies B and B are both holding. That means knowledge base is holding in that row, but A is not holding. And part of the reason why that can happen is B could have been caused by somebody else. I mean, by the way, implication is not actually causation, but people tend to look at it that way. And so if you look at it that way, A may not be the reason why B is true. B is true because some other reason. So in your case, essentially, you may be having runny nose because possibly you have Ebola virus. And if you have Ebola virus, everything will be runny, including the nose. Right? Okay? Now, here is a very interesting thing. So abduction is a bad guy. Abduction basically is not sound. If you are a medical doctor and you say, I only do deduction, do you think anybody will come to you? Is there any doctor in the land who can charge money for them to tell you, if you go and tell them, I have flu, can you check if I have runny nose? And they'll check for you. Would there be any doctor who would get money for that? No. In fact, abductive inference is extremely useful. Entire medical diagnosis is abductive inference. Seeing the symptoms, figuring out what the disease is. And I'm saying logic won't help you. So if you are pre-med students, you should leave the class right away. Okay, but I guess most of them are not. Okay. But it's worthwhile knowing that logic, first order, the propositional logic has its own limitations because the entailment notion is not the only kind of inference you want to do. You're actually sometimes interested in doing abductive reasoning, where abductive reasoning where you see the symptom and you want to figure out whether the cause holds. And in general, for that's where you wind up again doing probabilistic reasoning. In fact, you'll wind up using Bayes' rule to figure that out. The possibility that you, given that you have a runny nose, the probability that you have, flu is this much, and the probability that you have Ebola virus is this much. Okay? And that's basically what probabilistic reasoning will do, and logic won't help you. So abduction is actually, unsound. Then what else? These are all basically sound, but none of them are complete. None of them are complete. To say that something is not complete, what do I need to do? I need to give you at least one example case where you would admit that the truth table based computation of entailment will say the thing is entailed. And yet you don't see any one of these rules by themselves telling you that. Do you see what I'm saying? None of them by themselves will tell you that. So here is, that's fine. Okay, so this is actually, I guess, what is this one? So I was just showing that this particular rule, A implies B and not A, does not entail not B. I showed that there. I can remove this basically. Okay, so I'm saying that this rule, which is actually not called abduction, is in fact unsound because I computed this and I found that there are two rows, the yellow rows where knowledge base is true, but in only one of those yellow rows not B is true, the other it is false. Which means it's not a sound rule of inference. So to prove that something is sound, you use the truth tables. That's the first principles here. Okay? So the question, of course, the other thing that I was saying is none of them are complete, and the reason they are not complete, I just need to give you an example, which is this. I'll give you this simple example. Oh my God, I know why I wrote this. No, there are two people, Will and Jane, and they're trying to go to a party. If Will goes to the party, then Jane will go to the party. So W implies J. And if Will doesn't go, then Jane will still go to the party. Okay, so not W implies J. Now the question is, will Jane go to the party? It's a very hard question. You guys see that Jane will go to the party, right? Can you show that using any one of the single rules here? That's why they are not complete. It turns out that if you use all these rules together, one after other, you may be able to, in fact, you will be able to prove. But an interesting question is, can you just get one rule that is both sound and complete? Actually, here is another way I can deal with completeness. I can make something just complete if you don't mind sound. That's the rule called yes ma'am, it's true. Whatever you ask me, I'll say it's true. So if you say, is this theorem holding? Yes. Is this other theorem holding? Yes. Is this third theorem holding? Yes. If I do this, would I be complete? Because everything that you can prove to be entailed, I said entailed because I'm only saying entail, entail, entail. But am I sound? No, because there are certain things that are not entailed, I'm also telling them they're entailed. So getting just sound rules or just complete rules is possible. Especially, actually getting just sound rules is useful also. That's why we know names for these rules. Getting just complete rules is basically useless because you're just throwing stuff, and you can, in fact, that's unsound reasoning. That means you once in a while are saying some things are true when they are not. Some things are entailed when they are not. Okay, so one of the interesting questions is, can we get one single rule of inference called, which is both sound and complete? And it turns out that that rule is the resolution rule of inference. Okay, and the interesting thing is that resolution rule does have to do case analysis. The way you did this is, you did case analysis. Either Will go to the party or Will won't go to the party. If Will goes to the party, in all those times, you can prove that Jane will go to the party. In all the cases where Will doesn't go to the party, you can also prove that Jane goes to the party. So you have proved that Jane goes to the party, whichever way. That's what the case analysis did. Okay? And you don't, any of the other rules, none of the other rules provide that case analysis. Okay? And resolution allows you to show that case analysis, and I'll show that in a minute. One more thing. Okay. So by the way, so if you just use any of the sound rules, if you just use the set of all sound inference rules and try to prove entailment, that is called natural deduction. Natural deduction is basically what Greeks were talking about. Use modus ponens, modus tollens, and a rule. Every one of these funny things, every one of these things has a rule, a name. So A and B allows you to entail A. It also allows you to entail B. A or B and not A allows you to entail B. All of these have rule names. And if you use all these rules together, you will be actually able to prove everything that is provable. And not prove anything that's not provable. Both are important. So, by the way, the other thing that I wanted to make is at the, because we are into making everything connected to everything, soundness and completeness are connected to two other words that we don't talk about in AI much, but they talk a lot about in databases and information retrieval, etc. And learning, machine learning. Precision and recall. How many of you have heard of precision and recall? Which is which? Precision and recall are basically soundness and completeness. Which is which?
Recall is coverage, is basically what were the two words you had for now?
Soundness and completeness.
So completeness is recall.
Okay.
Soundness is
Precision. So anybody else questions that? So if you don't know, then you are, either way you learn something new. Okay? So if you didn't know the words precision and recall, now you know. Precision is basically soundness. Recall is completeness. Okay? And if you have 100% precision and 100% recall, then it is sound and complete. So normal, the only difference in information retrieval versus here is here you will say it's either sound or not sound. You don't say it's 90% sound. Precision, on the other hand, you say it's a certain percentage sound. It has 90% precision. Okay? Soundness basically is Boolean. Precision is a degree between 0 to 1. Completeness is again Boolean. Either it's complete or it's not complete. And recall is a generalization of completeness that is between 0 and 1. Okay? So that's what I remember. Okay, so all I'm going to do is just need something that does case analysis. And that would be the resolution rule of inference. So that resolution rule of inference is of the following form. If alpha and beta are actually propositions, they're not formulas. Okay, they're not sentences, they're just propositions. So if I have a formula alpha or beta, and then I have another sentence not beta or gamma, then I can basically take beta and not beta out and write alpha or gamma into my knowledge base. So whenever I see alpha or beta and not beta or gamma, I get to write alpha or gamma. So one thing is coming in different polarities. One is positive in this side and negative on that side. You take one, that particular thing just disappears and you get to write alpha or gamma. So similarly, if I have P and Q and not P or Q and not P or J, then I got to write Q or J. That's what resolution is. That's it. Very reasonable rule. Okay. First of all, how do you prove that it is actually sound? You have to construct a table like that. So you should make it a homework right after the class to write a little table for A, B, C. So A or B and A, B, C, yeah. A or B and not B or C are the two sentences you know. And then you should be able to show A or C. Okay? Actually, I just see whether the one that we did actually is that. Right? This one is resolution, right? Because I happen to know A or C and B are not C. So C and not C disappear and I get to write A or B. It took forever for us to prove this. We just proved. beforehand, before stating the rule. Do you understand that? So all we did in the first part of the class was actually proving the soundness of resolution rule. So you don't even have to do homework, it's actually there. It's the deductive closure of your notes, and you just have to produce it in the exam. Okay. Okay, so that's your resolution rule soundness. How do I prove its completeness? Completeness requires an inductive proof. I'm going to just ask you to read the proof in the textbook. Okay, there is a nice inductive proof which basically tells you how to construct the base case in the inductive case to show that everything that is entailed is actually shown to be true by the resolution, by application of resolution. Completeness proofs are always harder because you need to provide the inductive proof. Soundness proofs are easier because you just do this by looking at the proof there. Okay? So it turns out that resolution is a sound and complete rule of inference, and so if you just keep using the resolution rule, you should be able to prove anything that can be entailed. That is entailed by the knowledge base. So propositional theorem proving can just be done by using resolution. Furthermore, another very interesting thing is if indeed it is the case that resolution is such a general rule, then everything, there are two possible issues, two different issues now. One is, if it's such a general rule, how come it is written such that the sentences are of this form, A or B and not B or C? After all, I can have sentences like A and B, A implies B, A implies B and not C, all those sentences. And you're telling me that resolution rule is sound and complete, but it only works if the sentences are of this form. So what gives? What gives is it better be the case that everything can be compiled down to this form. Right? I mean, it's just like saying that your computer can only do Intel instruction set and C language can be run on your computer. That means C language ultimately becomes a bunch of Intel instructions, and there is a way of compiling. You see what I'm saying? So I will tell you in the next slide, this particular form, this form where every sentence in the knowledge base is a disjunction of literals. Disjunction means or, and a literal basically is either a proposition or the negation of the proposition. That would be called conjunctive normal form, CNF. So your database is a conjunction of these clauses. Each clause is a disjunction of literals. That's the assembly language. So if you write your knowledge base in any arbitrary propositional sentence form, you can compile it down into a set of clauses. I will show you how to do that. Once you compile it down, then basically you can just apply resolution. Okay? That's a very useful thing. And so in fact, we do have to consider that. And actually you can already see how this comes in. The one thing that you hated was this implication symbol. A implies B. But I already told you A implies B is nothing but not A or B. So already that thing is in the clausal form. Now you might be asking, what about A and B? Well, A and B is just two clauses, clause A, clause B. A or B, already it's in clausal form. Okay? A or B and C. A or B and C. You use De Morgan's laws. So A or B and C will be A or B and A or C. And then say A or B is one clause, A or C is another clause. I'll show that again in a minute, but you can see that there is a simple, straightforward procedure that you can use to convert the entire knowledge base into clausal form. Once you put it in the clausal form, you will actually be able to do resolution. By the way, those of you who said you had heard of satisfiability problem, if you think back to it, you would have thought it would have been introduced as satisfiability problem is given a set of clauses, CNF clauses, can you find the truth falsity assignments for the proposition such that all clauses will evaluate true? So satisfiability problem already uses the CNF clauses. Okay, that's the way it is. Okay, and so that is one question, which is how to convert any arbitrary knowledge base into clausal form. That can be done. I kind of just explained it to you in a minute. I sort of sketched the explanation, but I'll also show you in a minute. More fleshed out algorithm. The second question is, if indeed resolution is that general, is everything else, can you show it to be a special case of resolution? It must be, right? If it's one rule that actually captures everything, then every possible rule you can think of must be a special case of resolution. Okay, let's take some example. Let's take, for example, modus tollens, which basically is of the form A implies B, not B entails not, A implies B, not B entails not A. Remember, that's the modus tollens rule. Can you show that it actually follows from resolution? Yeah, it does, because what is A implies B? A implies B is not A or B. What is not B? Not B is just not B, because that's a clause by itself. Now if I resolve these two, B and not B go away, I get not A. Proved. You can take every other thing, like A or B and not A implies not B. I'm sorry, A or B and not A implies B. Entails B, right? You can do that too. A or B and not A and not A goes away and B remains, and that's by resolution, and that was just what the other rule is saying. So every other rule in propositional inference that you know of is just a special case of resolution. Okay? Okay, so what I'm going to do is to actually show here a simple example. Okay, first of all, so let me show you a simple example. So here will goes, Jane will go. If will doesn't go, Jane will still go. So this will be written as W implies J, but W implies J is nothing but W or J. And this will be written as W, not W implies J, not W implies J is nothing but W or J. Right, because A implies B is not A or B. And so not A implies B is not of not A, which is A or B. Okay, so I have this, not W or J, W or J. That's my knowledge base. So at this point, I can do either forward or backward reasoning. Forward basically is just take existing clauses, combine them, and see if I can get J. Okay, that's forward. So in this particular case, W or J, not W or J,